You have almost certainly seen this one already. The ball that gets cut into a few pieces and rebuilt into two balls the same size as the first. A pea that becomes the sun. It shows up in every corner of the internet, dressed as a magic trick. A fun little fact about infinity. A thing that makes you say that is strange and then scroll on. And if that is the version you came here for, you honestly already have it. You can close this right now and lose nothing. But there is one thing those versions never tell you, and it is the only part that actually matters. The two men who proved this did not build it to amaze you. They built it as a weapon, to destroy a single assumption buried at the very bottom of mathematics. The assumption survived. They lost. And the reason they lost is that pulling that one assumption out would have collapsed half of modern mathematics along with it. So the entire field looked at a proof that you can make something out of nothing, agreed it was a monster, and quietly decided to keep it anyway. Once you understand what they chose and what it cost the people who found it, and why no one who came after could ever prove the choice was right, the cute little ball trick stops being cute. It becomes the most unsettling thing anyone has ever shown you about the ground under your feet. So get comfortable. If you are new here, this is Fault Lines, and this is the kind of thing we do. Subscribe or join if you want more of them. And there is a Patreon where these go deeper and wider, across physics and history and the quiet places where the foundations do not quite hold. Stay to the end, because by the time we reach what a logician named Tarski proved about truth itself, you will understand why mathematics, the one thing we built to be certain, cannot tell you whether the ball can really be split in two. Let's start where it started. Take a solid ball, a billiard ball, an orange, a cannonball. The size does not matter for what I am about to tell you. Cut it into 5 pieces, not slices, not wedges, 5 pieces. Now pick those pieces up and move them around. You are not allowed to stretch them. You are not allowed to bend them, inflate them, or add a single point of new material to them. You are allowed to do 2 things and only 2 things. You may rotate a piece, turning it in space the way you would turn a key. And you may slide it, moving it from one place to another the way you slide a chess piece across a board. Rotations and slides, nothing else. And when you have finished rearranging those 5 pieces, you are no longer holding one ball, you are holding 2. Each of them exactly the same size as the ball you started with. The same volume, the same solidity, the same everything. 2 complete balls where a moment ago there was one, and you added nothing, and you stretched nothing, and you cheated in no way at all. I want to be precise about what kind of claim that is, because everything depends on you understanding it correctly from the first minute. That is not a magic trick. It is not an optical illusion. It is not a riddle with a clever catch hiding in the wording. It is not a loose metaphor for something subtler that I am going to walk back in 10 minutes. It is a theorem. A proved, published, peer-reviewed result in mathematics sitting in the literature since 1924. As solid and as permanent as the statement that there is no largest prime number. Mathematicians do not argue about whether it is true. It is true the way a thing is true once it has been proved, which is the most final kind of true there is. Its name is the Banach-Tarski theorem, and the men who proved it were not cranks working in the margins. They were 2 of the most serious mathematicians of the 20th century, and one of them has an entire branch of modern mathematics named after him. And here is the part that I need you to sit with before we go anywhere near how it works. The size of the ball genuinely does not matter, and neither does the size of the 2 balls you end up with. The same theorem, in a slightly stronger form, says this. You can take a ball the size of a pea, cut it into a finite number of pieces, rotate and slide those pieces, and reassemble them into a ball the size of the sun. Not a ball that looks like the sun, not an approximation. A solid ball with the exact radius of the sun, built entirely out of the pieces of a pea, with nothing added. The pieces of the pea, rearranged, are enough to fill the sun completely. This is not a different theorem. It is the same one, and it has a name too. Mathematicians call it the strong form, and they prove it as a casual consequence of the first result, almost as an afterthought, the way you would mention that since you can double your money once, you can obviously double it again. You are having a reaction to this right now, and the reaction is correct, and I want to name it before we lose it. Something in you is saying that this is impossible. Not unlikely, not strange. Impossible, in the strong sense, the sense in which 2 plus 2 cannot be 5. Because you know something, deep below the level of argument, that you have known since you were a small child playing with clay or water or sand. You know that you cannot get more stuff by cutting. You can cut a thing into 1,000 pieces, and you still have exactly the same amount of thing. The pieces can be rearranged into a different shape. Sure, you can squash the clay into a snake or a ball, but the amount never changes. That is not a theory you hold. It is closer to the floor you stand on. It feels less like a belief and more like a basic condition of living in a physical world. That floor is about to come up, because there are 3 separate things you believe right now, and you believe them so completely that you have probably never once said them out loud, and the Banach-Tarski theorem breaks all 3 of them. You believe that cutting and rearranging cannot change how much there is. You believe that volume, the amount of space a thing takes up, is a real and fixed property of an object. And underneath both of those, quietly, you believe the most basic thing of all, which is that every piece of a solid object has a size, that a chunk of a ball is a certain amount of ball. Even if it is a strange and jagged chunk, even if you have not measured it, even if you never could, you believe that the size is sitting there, waiting, whether or not anyone ever finds out what it is. Not one of those 3 beliefs survives this story, and the order in which they fall is going to matter, because each one falls for a different reason, and the reasons get worse as we go down. I have spent an unreasonable amount of time reading about this, far more than is healthy, and I will tell you honestly that the ball is the easy part. The ball is the thing they put on the poster. Doubling a sphere is the magic trick they show you at the door to get you to come inside. It is genuinely strange, and we are going to take it completely apart, slowly, until you can see every gear turning and you understand exactly why it has to be true. But it is not the thing that should disturb you. The thing that should disturb you is sitting one level underneath the ball, in the foundations, in the bedrock assumptions that all of mathematics is built on. Because in order for you to be allowed to double that ball, something has to be true about the deepest layer of mathematics. A particular rule has to be switched on. And the mathematicians who built the modern foundations looked directly at this theorem, understood exactly what it was telling them, understood exactly what that rule was costing them, and they decided to keep the rule anyway. They saw the price. They paid it, on purpose, and they did not tell you. That is the real story here. Not that a ball can be doubled, that the people who write the rules of mathematics found a place where the rules produce something that should not be allowed to exist, and rather than change the rules, they decided that the impossible thing was the price of doing business, signed the contract, and moved on. The ball is just the receipt. So let us start with the ball, because you cannot understand the contract until you understand exactly what it bought. And to understand the ball, we have to go back further than 1924. to a quieter and stranger result that almost nobody outside of mathematics has ever heard of. A result that did not double anything, that did not make headlines, that simply pointed at a single set of points on a number line and asked one question that turned out to have no acceptable answer. The question was this: how big is it? And the universe of mathematics, for the first time, refused to say. The year is 1905, the place is Italy, and the man is Giuseppe Vitali, 30 years old. A mathematician of real talent who would spend much of his life teaching in secondary schools because the academic posts went to better connected men. Vitali was not trying to break the universe. He was trying to answer what looked like a reasonable, almost boring housekeeping question. Mathematics had just spent several decades building a careful theory of how to measure things. Not measure with a ruler, but measure in the deep sense. Given any collection of points, any set at all, how much room does it take up? What is its length if it sits on a line? What is its area if it sits on a plane? What is its volume if it sits in space? This sounds simple, and for ordinary shapes it is. A line segment from 0 to 1 has length 1. A square with sides of length 2 has area 4. You learned this, and it never gave you a moment of trouble. But mathematicians are not satisfied with ordinary shapes. They wanted a rule, a single consistent rule that would hand you the size of any set whatsoever. Not just the nice ones, the jagged ones, the scattered ones, the sets made of infinitely many disconnected specks of dust. A French mathematician named Henri Lebesgue had just built the most powerful version of such a rule, and it was a genuine triumph, and it is still the foundation of how measurement works in mathematics today. The Lebesgue measure could handle almost anything you threw at it. The word almost is going to do an enormous amount of work in this story. Here is what everyone wanted to be true. They wanted measurement to obey 3 rules, and the 3 rules are so reasonable that you will agree with all of them instantly. First, the measure of a simple line segment should be its ordinary length. The segment from 0 to 1 has size 1. Nothing clever there. Second, if you take a set and slide it somewhere else without rotating or resizing it, its measure should not change. Move a thing from here to there, and it is still the same size. This is so obvious it feels insulting to state. Third, if you take a set and chop it into separate pieces that do not overlap, the sizes of the pieces should add up to the size of the whole. Cut something apart, add up the parts, you get the total back. Conservation, the thing you have believed since the clay and the sand. Those 3 rules are the entire dream. A measure that gives line segments their length, that does not care where you put things, and that adds up properly when you cut. If you could build a rule like that, and have it work on every possible set of points, then measurement would be complete. Every set would have a size. The universe would be fully weighed. Vitali proved that this dream is impossible, not difficult, not currently out of reach, impossible forever, as a matter of logic. He proved that there exists a set of points so strange that no rule obeying those 3 reasonable conditions can assign it any size at all. Not a size of 0. Not an infinite size. No size. The question how big is it has no answer that does not produce a contradiction. And he built this monster out of almost nothing. Let me show you the construction, because it is the seed of everything that follows, and once you see it, the ball stops being magic and starts being inevitable. Take the number line, all the real numbers. Now group them into families. 2 numbers go in the same family if their difference is a rational number, a number you could write as a fraction. So the number 0 and the number 1 are in the same family, because their difference is 1, which is a fraction. The square root of 2 and the square root of 2 plus 3 are in the same family, because their difference is 3. But the square root of 2 and the number 0 are in different families, because the square root of 2 is irrational and cannot be written as a fraction. Every real number sits in exactly one of these families, and there are infinitely many families, an uncountable infinity of them, each family itself an infinite scattering of points spread across the entire number line. Now Vitali does the thing that is going to matter for the rest of this story, and I want you to watch his hand very closely as he does it, because this single move is the whole game. From each family, he picks one number, just one representative from each family, all of them chosen to lie between 0 and 1. He gathers those chosen representatives together into a single set. That set is the Vitali set, and the Vitali set has no size. You can prove it has no size in a few lines, and the proof is one of those things that feels like watching a magician show you the trick and the trick getting worse instead of better. Take the Vitali set and make copies of it, shifting each copy by a different rational number. Because of the way the families were built, these shifted copies do not overlap, not at a single point, and together they cover the entire number line with nothing left out. Now apply the 3 reasonable rules. Sliding does not change size, so every shifted copy has the same measure as the original Vitali set, whatever that measure is. Call it some number. The copies do not overlap, so their sizes must add up. And there are infinitely many copies, all the same size, adding up to cover a stretch of the line that has a perfectly ordinary finite length. So you are adding up infinitely many copies of the same number and getting a finite, non-zero total. There is no number that does this. If the shared size is 0, then infinitely many zeros add up to 0, and the line has length 0, which is false. If the shared size is any positive number at all, then infinitely many copies of it add up to infinity, and the line is infinitely long where it should be finite, which is also false. Every possible answer is a contradiction, so there is no answer. The Vitali set has no measure. It is, in the exact technical term, non-measurable. I need to stop here for a moment and make sure the weight of this lands properly, because it is easy to let it slide past as a technicality. We did not fail to measure the Vitali set because it was too complicated, or because our instruments were not good enough, or because nobody clever enough has tried yet. We proved that it cannot be measured, that the very concept of size does not apply to it, the way the concept of color does not apply to a sound. There is a set of points sitting on the ordinary number line, built out of ordinary numbers, and it is not large, and it is not small, and it is not anything, because size is simply not a property that it has. The number line, which you think of as the most well-behaved object in all of mathematics, the thing you learnt about before you could ride a bike, has objects living inside it that have no size. And they are not rare. In a precise sense that mathematicians can make exact, almost every set is like this. The measurable sets, the ones with sensible sizes, are the strange and special exceptions. The unmeasurable monsters are the overwhelming majority. You have just never met one, because you cannot build one without doing the exact thing Vitali did. It is worth pausing on just how badly outnumbered the well-behaved sets are, because the imbalance is not close, and it is not a matter of opinion. Think about how a set could ever be described. Any description, any rule, any defining property you could state is in the end a finite string of symbols, a sentence in some language. And there are only so many finite strings of symbols. Endlessly many, yes, but only countably many of them, the same tame size of infinity as the counting numbers, because you could in principle list them all in order of length and then alphabetically, and never miss one. So there are only countably many possible descriptions of sets, ever, in any language, human or otherwise. but the number of sets of real numbers is not countable. It is a strictly, savagely larger infinity, larger even than the infinity of the real numbers themselves. Set those two facts side by side, and the floor tilts. There are vastly, incomprehensibly more sets than there are possible descriptions of sets, which means almost every set, in the most literal sense the word almost can carry, can never be described by any rule, any formula, any finite sentence in any language at all, because there are nowhere near enough descriptions to go round. The sets you can name, the intervals and circles and familiar shapes, the sets you have ever once thought about, are a vanishingly thin film floating on an ocean of sets that have no names and never will. And it is out there, in that nameless ocean, that the non-measurable monsters live, almost all of them, unreachable and undescribable, and yet provably present. Vitali's only real trick was to use the axiom of choice as a net, to haul one of them up into the light without ever being able to say which one he had caught. And here is the thing Vitali did, the move I told you to watch. To build his set, he had to pick one representative from each of infinitely many families, not according to a rule. There is no rule. There is no formula that says here is the right representative from each family. The families are too wild and too numerous for any formula to reach. He simply asserted that a choice could be made, all at once, across infinitely many families, with no procedure for making it. He reached into infinitely many boxes simultaneously and pulled out one item from each, without any way of saying which item he pulled. That assertion, that you are allowed to make infinitely many arbitrary choices at once, with no rule to guide them, has a name. It is called the axiom of choice. Remember it. It is going to come back. And when it comes back, it is going to be holding the whole story in its hands. But in 1905, almost nobody noticed, because Vitali's monster, for all its strangeness, did not do anything alarming. It just sat there being unmeasurable, a curiosity, a warning sign on a road almost no one drove down. It said that not every set has a size. It did not say you could double a ball. To get from a set with no size to two balls where there was one, mathematics needed to find something far stranger than a number with no length. It needed to find a shape that could eat itself and come back whole. And the first person to find one was a man whose own life would end in a way so dark that it is difficult to set next to the elegance of what he discovered. His name was Felix Hausdorff, and what he found in 1914 was not a set that had no size. It was a sphere that contained two copies of itself. Before we get to Hausdorff and the sphere, you need to see one piece of machinery work on its own, away from any ball, because it is the actual engine of the entire paradox, and everything else is decoration bolted onto it. And to get your intuition ready for it, I want to show you a smaller, gentler strangeness first, one that has been used to unsettle students for over 100 years. It is usually told as a story about a hotel. Imagine a hotel with infinitely many rooms, numbered 1, 2, 3, and on forever, and imagine every single room is full. A new guest arrives wanting a room. In an ordinary hotel, this is the end of the conversation. But this hotel has a trick. The manager asks every guest to move to the room numbered 1 higher than their current room. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3, and so on, all of them shifting up by 1 at the same instant. Now every guest still has a room, nobody has been thrown out, and room 1 is empty. The new guest checks in. The hotel was completely full, and it absorbed a new guest, and it is still exactly the same hotel. Nothing was added. The guests were only rearranged. Sit with what just happened, because it is the same crime as the ball, only smaller. A collection that was complete became a collection with room to spare, and the only operation performed was moving things around according to a rule. The infinite hotel can swallow a guest because there is no last room for the displacement to fall off the end of. Shift everything up by one, and the overflow has nowhere to overflow to. It just keeps going. Infinity does not conserve the way finite things conserve, and that single fact that an infinite collection can be slid into a proper part of itself with room left over is the crack that the entire Banach-Tarski theorem is going to climb through. The ball has infinitely many points. That is the only reason any of this is possible. A ball made of finitely many atoms could never be doubled, and we will come back to that, because it is the single most important thing to understand about what this theorem does and does not say. But a ball made of infinitely many dimensionless points is a kind of hotel, and hotels like this can be made to misbehave. The hotel only absorbs one guest though, or finitely many, or even a countable infinity of them. It cannot double itself. To double something you need a richer and more violent kind of infinity, and that is the free group. And I am going to build it for you out of nothing but 4 symbols and a rule. Take 2 symbols and call them A and B. Allow yourself their opposites, which we will write as A inverse and B inverse, with the understanding that a followed immediately by a inverse cancels out to nothing, the way taking 1 step left and then 1 step right leaves you where you started. Now write down every possible string you can make from these 4 symbols, with the single rule that you never write a symbol immediately next to its own opposite, because that would just cancel. So A, then ab, then abab, then abba inverse, then babab. Every finite string of these 4 letters with no cancellation showing. This infinite collection of strings, with the operation of sticking one string onto the end of another and cancelling whatever cancels, is called the free group on 2 generators. The word free means there are no relations, no surprises, no secret equalities. 2 strings are equal only if they are literally the same string of letters. It is the most unconstrained, most rigid, most maximally complicated object of its kind, and it is about to eat itself. Here is how. Take the whole free group, every string there is, and sort every string into one of 4 buckets, based on the very first letter you see when you read it from the left. Bucket 1 holds every string that starts with A. Bucket 2 holds every string that starts with A inverse. Bucket 3 holds every string that starts with B. Bucket 4 holds every string that starts with B inverse. Every non-empty string lands in exactly 1 bucket, because every string has exactly 1 first letter. So far, this is just filing. Now watch. Take bucket 2, the bucket of all strings that start with an inverse, and perform a single operation on every string in it. Stick the letter A onto the front of each one. What happens? If a string starts with an inverse, putting an A in front of it cancels that A inverse, and you are left with whatever came after. And what comes after can be anything at all, anything that does not start with A. Because if it started with A, the original string would have had A inverse followed by A, which cancels and is not allowed. So when you take the entire bucket of strings beginning with A inverse and shove an A onto the front of each, you do not get back a small set. You get back almost the entire group. You get every string that does not begin with A. You get bucket 2 and bucket 3 and bucket 4 and the empty string 2, all of it, the whole group except the single bucket of strings that begin with A. 1/4 of the group, shifted by a single letter, expands to cover 3/4 of the group plus the empty string. Let me say what that means in plain terms, because it is the most important sentence in the mathematical core of this entire story. A piece of the group, when you simply slide it by multiplying by A, becomes almost the whole group. And the same trick works on bucket 4, the strings starting with B inverse. Shove a B onto the front of each, and that quarter also blossoms into the whole group minus 1 bucket. So here is the doubling, laid out bare. Keep bucket 1 as it is. Take bucket 2 and slide it by A, and it fills out into nearly the entire group. Just from those two pieces, bucket 1 sitting still and bucket 2 slid over, you have reconstructed the whole group. Then keep bucket 3 as it is, take bucket 4 and slide it by B. And from those two pieces, you reconstruct the whole group a second time. You cut the group into 4 pieces, you slid 2 of them, and you ended up with 2 complete copies of the group you started with. 2 for 1. No stretching, only sliding. The free group is paradoxical in the exact technical sense. It can be cut into finitely many pieces and reassembled, by motion alone, into 2 copies of itself. Let me make that concrete with one example you can follow on your fingers, because it stays slippery until you actually walk it. Reach into bucket 2 and pull out the string A inverse B. It starts with A inverse, so bucket 2 is where it belongs. Now shove an A onto its front. The A meets the A inverse, they cancel, and you are left with just B. A string that starts with B and now sits in the territory of bucket 3. Pull out another one, the string A inverse BA. Shove an A on the front, the A inverse dies, and you are left with BA, again a string starting with B. Pull out A inverse B, which is perfectly legal since A inverse next to A inverse does not cancel. Shove an A on the front, one A inverse dies, and you are left with a inverse B, a string starting with a inverse. Watch where the results are landing. Some come out starting with B, some with B inverse, some still with A inverse, but not a single one comes out starting with A. Because to start with a it would have had to begin life as a inverse A, which cancels and is not a legal string. So the whole bucket, shoved by one letter, rains down across every part of the group except the strings that start with A, and it covers that territory completely, because every string not starting with A is just an A inverse waiting to be uncovered. A quarter of an infinite object swells into 3/4 of it, and nothing was added. The only thing that changed was where each string sits after a single shove. This is the whole engine. Everything else is plumbing. If you can find a free group hiding inside the rotations of a sphere, then the sphere inherits the curse. The sphere becomes paradoxical because the rotations that move it around are secretly the strings of a free group, and the free group can be cut up and doubled, so the sphere can be cut up and doubled. The only question left is whether such a free group actually lives inside the rotations of 3-dimensional space, and the answer, found by a man whose mind was as elegant as his death was terrible, is yes. It is hiding in plain sight, and you can write it down with 2 specific rotations turned through one specific angle, an angle whose cosine is exactly 1/3. Felix Hausdorff was born in 1868 in what is now Wrocław, into a wealthy Jewish merchant family, and for the first part of his life, he did not look like a man who would reshape the foundations of mathematics. He wrote poetry. He published a book of aphorisms and a stage play, both under the name Paul Mongre, and the play was performed in something like 30 German theatres. He was a cultured, witty, slightly melancholy man who loved music and philosophy and the writing of Nietzsche, and who came to serious mathematics relatively late and then turned out to be one of the great pioneers of the entire field of topology, the study of shape and space and nearness. His textbook on set theory, published in 1914, was the book that taught a generation how to think about infinite collections of points. And buried inside that same book, almost as a side remark, was the result that made Banach-Tarski possible. What Hausdorff proved is this: take the surface of a sphere, the skin of a ball, not the solid inside, but just the outer shell. You can break that surface into a small number of pieces such that some of the pieces are simultaneously congruent to each other and congruent to combinations of the others, in a way that is flatly impossible for any ordinary notion of area. In the cleanest version, he split the sphere into 3 pieces and showed that the first piece was congruent to the second and congruent to the third, and also congruent to the second and third stuck together. Read that again slowly. One piece is the same as another piece. It is also the same as a third piece. And it is also the same as those other 2 pieces combined. A thing is congruent to 1/3 of the sphere and to 1/2 of the sphere at the same time, because it equals a single piece and it also equals 2 pieces joined. That cannot happen if those pieces have areas, because a piece cannot have both 1/3 of the total area and 1/2 of the total area, so the pieces do not have areas. They are non-measurable, the children of Vitali's monster, and Hausdorff had found them living on the surface of an ordinary sphere. How did he do it? He did exactly what I showed you with the free group, except he hid the free group inside rotations. He found rotations of the sphere that, when you string them together, never accidentally return to where they started unless you undo them step by step. In other words, he found rotations that behave like the strings A and B with no secret relations, no surprise cancellations. Those rotations generate a free group sitting inside the rotations of the sphere, and that free group is paradoxical, so its shadow on the sphere is paradoxical too. The standard way to write down such rotations, the version you will find in the textbooks today, uses 2 rotations through an angle whose cosine is exactly 1/3, an angle of about 70.53 degrees, taken about 2 perpendicular axes. There is nothing mystical about 1/3. Other angles work. Hausdorff's own original choice used different angles. What matters is only that the rotations are incommensurable in the right way, that no combination of them sneaks back to the identity, so that the group they generate is genuinely free and genuinely able to double itself. There was one piece of dirt Hausdorff had to sweep aside, and it matters, because it is the kind of honest detail that the simplified versions leave out. Every rotation of a sphere holds 2 points completely still, the 2 points where the axis of rotation pierces the surface, like the north and south poles of a spinning globe. Those fixed points break the trick, because the free group machinery needs every point to move freely. So Hausdorff had to first remove a countable collection of these troublesome fixed points, perform his paradoxical decomposition on what remained, and then deal with the leftover points separately. Removing them sounds like it should ruin everything, the way tearing a page out of a book should leave a gap. But it does not, and the reason it does not is the infinite hotel all over again. A countable set of missing points can be absorbed back in by a clever rotation, shifted around an infinite cycle until the gaps close up and the sphere is whole again. No holes, no scars. Hausdorff used that trick to clean up after himself, and the sphere came out perfect. So by 1914, the surface of the sphere was already paradoxical. The astonishing thing, the thing that genuinely surprises me every time I think about it, is that it then took 10 years for anyone to take the obvious next step. Hausdorff had doubled the skin. The solid ball is just the skin plus everything inside it, every nested shell from the surface down to the center, like the layers of an onion. If you can double the outer skin, you ought to be able to double every shell at once, and therefore double the whole solid. It is not quite that simple, because of the center point and a few technical wrinkles, but it is close to that simple. And the two men who finally did it, who carried Hausdorff's paradox down from the surface into the solid interior and out the other side into two whole balls, were a Polish mathematician of almost mythical natural genius and a young logician who would later become one of the most important thinkers about truth and language in human history. But before I tell you who they were, I want to finish the machine, because we are one step away from the doubled ball, and I do not want to leave the gears half assembled. Here is the whole construction in one breath. Take the solid ball, strip away the center point, and set it aside for a moment. Look at the rotations through the cosine 1/3 angles, which form a free group. Use that free group to sort almost every point of the ball into a handful of pieces, the same way we sorted the strings into buckets. The sorting is the choice move, Vitali's move, reaching into infinitely many orbits and picking one point from each to anchor the construction, which is why the axiom of choice is standing right there at the heart of it. And we will come back to that with the seriousness it deserves. Once the points are sorted, rotate two of the pieces, the way we slid two of the buckets, and each of them fans out to refill an entire ball. Reattach the center point with one more sleight of hand from the infinite hotel. And now you are holding two solid balls, each identical to the one you started with, each complete, each real, built from a finite number of pieces of the original by nothing but rotation and sliding. How few pieces? This is one of those questions where the answer has a sharpness that I find genuinely beautiful and also slightly menacing. In 1947, a mathematician at Berkeley named Raphael Robinson proved that the absolute minimum number of pieces needed to double a solid ball is 5. Not around 5. Exactly 5, and one of those 5 is a single solitary point, the leftover center we kept setting aside. 4 pieces if you are willing to ignore that one center point. You cannot do it in 3. Robinson proved that the floor is 5, and that the floor cannot be lowered, ever. 5 strange, dust-like non-measurable pieces, and a sphere becomes 2 spheres. It is not a vague infinite mess. It is a precise, minimal, almost surgical procedure, and the precision is somehow worse than vagueness would have been. Vagueness you could dismiss. 5 is a number you have to live with. Before I take something away from you, I want to make good on the promise from the very beginning, the P and the sun, because it is not a separate marvel. It is the same trick, refusing to know when to stop. Once you can turn one ball into 2 identical balls, you can take one of those and turn it into 2 again. And now you have 3, and again, and now 4, and there is nothing to stop you running this as many times as you please. Finitely many doublings, and you have as many copies of the original ball as you want. 100 of them, 1 billion of them, each one whole, all conjured from the single ball you started with. That alone should be enough to cover a far larger ball with room to spare, the way a bag of marbles can fill a space much bigger than any one marble. But mathematicians proved something cleaner and stronger than just piling up copies. And it is worth seeing, because it is where the P and the sun become literally exact rather than approximate. There is a principle, a cousin of an old result called the Schroeder-Bernstein theorem, which says this: suppose you have 2 shapes, and you can cut the first into finitely many pieces that fit inside the second. And you can also cut the second into finitely many pieces that fit inside the first. Then the 2 shapes are equi-decomposable, which means you can cut either one into finitely many pieces and reassemble those exact pieces into the other perfectly, with nothing left over and nothing missing. Now think about the P and the sun. The P obviously fits inside the sun. That direction is trivial. And the sun fits, in pieces, inside the P, because by doubling the p enough times you can manufacture enough ball to account for every point of the sun and then fold it back down to fit. Both directions hold. So the principle clicks shut, and it delivers its verdict. The p and the sun are equidecomposable. A ball the size of a pea can be cut into a finite number of pieces and reassembled, by rotation and sliding alone, into a solid ball the size of the sun. Not approximately, not most of it. The exact ball, every point of it, out of the pieces of the pea. The size of a thing, in this mathematics, places no limit at all on what its pieces can become. That is the strong form, and it falls out of the doubling almost for free, which is the most unsettling thing about it. The hard part was making two balls from one. Making the sun from a pea is just bookkeeping after that. Now I have to stop and take something away from you, because by this point in the story, a particular hope has usually started to form, and it is wrong, and the way in which it is wrong is the single most important thing to understand about what this theorem does and does not say. The hope goes like this. If you can double a ball, then somewhere, somehow, in principle, you could double anything. A bar of gold, a loaf of bread, a barrel of oil. The dream of getting something for nothing is very old and very deep, and a theorem that says one ball becomes two balls sounds like the dream finally written down in the language of proof. I need to close that door completely, because it is locked, and it was locked from the beginning, and the key was thrown away before Banach-Tarski ever started. You cannot double a bar of gold. You cannot double anything made of matter. Not because it is technically difficult, not because our tools are not good enough yet, but because the theorem requires something that physical matter does not have and can never have. The entire construction depends on the ball being made of infinitely many points, each one of them a perfect mathematical point with no size at all, packed together with infinite density, divisible without end. You can cut such a ball into the strange non-measurable dusts, because between any 2 points there are always infinitely more, and you never run out, and there is no smallest piece. A bar of gold is not like that. A bar of gold is made of atoms, a finite number of them, something like a few times 10 to the 24th atoms for a bar you could hold. And an atom is not a dimensionless mathematical point. It is a physical object with a size, and below it there are smaller physical objects with sizes, and at the bottom, as far as physics can tell, the divisibility stops. There is no infinite dust hiding inside a gold bar. There are only finitely many pieces, and finitely many pieces obey exactly the conservation rules you always believed in. The infinite hotel needs infinitely many rooms. Matter only ever has finitely many. The whole trick dies the instant you try to run it on anything real. So the theorem does not threaten the conservation of mass, and it does not let you counterfeit gold, and it is not a loophole in physics. It lives entirely in the world of pure mathematics, in the realm of ideal points and infinite sets. And it never crosses over into the world of atoms. I want to be very clear about this, because the simplified versions of the story love to imply otherwise, love to hint that maybe one day, with enough cleverness, you could duplicate physical objects, and that hint is a lie. Defining a strange mathematical cut on an infinite set of points is no more a physical procedure than the act of multiplying a number by 2 is a physical procedure. You can double the number that describes the mass of an object on a piece of paper. That does not double the object. Banach-Tarski is in a sense a statement about what the word cut is allowed to mean when you let it operate on a true mathematical continuum. And the answer is that it is allowed to mean something so violent and so strange that the ordinary world, made of ordinary stuff, is simply not invited. There is a second thing I need to take away from you, and it is subtler. The word paradox is doing a lot of damage here, because in ordinary speech, a paradox is a contradiction, a place where the reasoning eats itself and something has gone wrong. That is not what this is. The Banach-Tarski paradox contains no contradiction. Nothing in it is broken. Every step is valid, every inference is sound, and the conclusion follows with total rigor from the assumptions. It is called a paradox only in the older and gentler sense of the word, meaning a result that runs violently against intuition while being completely true. It does not break mathematics. It does not reveal a flaw in logic. It is mathematics working perfectly, doing exactly what the rules permit, and arriving somewhere that your intuition refuses to follow. The discomfort you feel is not the discomfort of catching a liar. It is the discomfort of being shown that the rules you trusted lead somewhere you did not agree to go. The rules are fine. It is the destination that is the problem, and the destination is not a mistake. It is a theorem. And the last thing, the hardest thing to hold in your head, the 5 pieces are not chunks. When I say cut the ball into 5 pieces, every instinct you have pictures something like 5 wedges of an orange, or 5 irregular lumps, pieces with edges and surfaces and definite shapes. Erase that picture. The pieces are non-measurable sets, the children of Vitali's monster, and they are not lumps of anything. Each one is an infinitely intricate scattering of individual points, spread throughout the ball like a mist, with no surface, no edge, no shape you could ever draw or hold, or even imagine clearly. They interleave with each other at infinite fineness, so that around every point of one piece there are points of the others, packed in arbitrarily close, forever. You could never carry one of these pieces across a room, because there is nothing to pick up, only a ghostly distribution of locations that no physical object could ever embody. They exist as ideas, as sets, as decisions made by the axiom of choice about which point goes where, and they exist in no other way at all. When the textbooks draw the Banach-Tarski decomposition as 5 neat-colored regions, they are lying to you for your own comfort, because the truth cannot be drawn. The truth has no picture. That is part of what makes it so hard to hold, and part of why almost nobody who has heard of this theorem actually understands what it claims. That is the trick they show you at the door. That is the receipt. Now I am going to take you to the men who signed it, and to the city where they signed it, because the place where this theorem was born is one of the most extraordinary and one of the most tragic settings in the history of mathematics. And what happened to the people in it is impossible to separate from what they discovered. They proved that you could pull a second world out of the pieces of this one. And then the actual world they lived in was taken apart around them, piece by piece, and not put back together. In the summer of 1916, a mathematician named Hugo Steinhaus was walking through the Planty Gardens in Krakow, a ring of green that wraps around the old city, and he heard something that stopped him. 2 young men were sitting on a bench, and they were talking, and the words drifting over to him were Lebesgue integral. This was wartime, and the Lebesgue integral was perhaps 2 or 3 years old as a piece of serious mathematics, the cutting edge of the cutting edge, and here were 2 unknown young men discussing it casually on a park bench, as though it were the weather. Steinhaus introduced himself. One of the young men was Stefan Banach, 24 years old, with no university degree, who had been raised by a laundress, who had never known his mother, the illegitimate son of a man who gave him the surname of the woman who took him in. Banach had no formal mathematical training to speak of. He had been working as a tutor and was, by his own account, drifting. Steinhaus would later say that the discovery of Banach was the greatest discovery of his life. And Steinhaus was a man who discovered a great many things. He took Banach under his wing, and within a few short years, the laundress's son with no degree had become the most original mathematician in Poland, and arguably one of the most original in the world. Banach settled in the city of Wow, a city that has been Polish and Austrian and Soviet and Ukrainian, that has been called Lemberg and Lviv and Wow, and that in the years between the two world wars was one of the most intense concentrations of mathematical talent ever assembled in one place. Banach and Steinhaus and a cluster of brilliant younger men built what is now called the Wow School of Mathematics, and they did not do their work in quiet offices. They did it in a coffee house. There was a cafe called the Scottish Cafe, the Cowiania Skokke, and the mathematicians of Wow would gather there for hours, for entire days, drinking coffee and arguing and writing mathematics directly onto the marble tabletops in pencil, because the marble could be wiped clean by the staff at the end of the night. You can see the problem with this. A day of work by some of the finest minds in Europe, wiped away with a wet cloth at closing time. Banach's wife eventually solved it. She bought a large notebook and left it with the head waiter, and when the mathematicians wanted to record a problem, they would ask for the book, write the problem down, and sometimes a proposed prize for whoever could solve it. This notebook became known as the Scottish Book, and it is one of the most famous documents in mathematics. It contains 193 problems written down between 1935 and the early years of the war, and many of them shaped entire research programs for decades afterward. The prizes are part of the legend. They ranged from a small beer to a bottle of wine, and in one famous case, problem number 153, posed by Stanislaw Mazur in November of 1936, the prize offered was a live goose. The problem sat unsolved for 36 years. It was finally cracked in 1972 by a Swedish mathematician named Per Enflo, and Mazur, true to his word, presented Enflo with a live goose in a ceremony broadcast on Polish television. A man received a living bird as payment for solving a problem written in a coffee house by mathematicians, most of whom were, by then, decades dead, many of them murdered. The goose is funny until you remember who was not there to laugh. I want to stay in that coffee house a little longer, because the Scottish Cafe was not a quaint detail on the side of the real work. It was where a particular way of doing mathematics lived, and that way of doing mathematics has never quite existed again anywhere. The sessions were marathons. Stanislaw Ulam, one of the younger members of the school, a man who would later leave for America and become one of the central figures in the design of both the atomic bomb and the hydrogen bomb, remembered a single mathematical session between Banach and Stanislaw Mazur that ran for 17 hours without a real break, the two of them at a marble table, arguing and calculating, stopping only because the cafe was closing for the night, the problem still unsolved when they finally went home. That was not unusual. That was the rhythm of the place. Banach, in particular, seemed to need the noise. He could not work in the quiet of a study or a library. He worked best in the clatter and smoke and chatter of bars and cafes, surrounded by talk. With a glass nearby and a cigarette going, scribbling on the marble, or on scraps of paper, or on the backs of bills. And by every account, the louder and more crowded the room, the more freely his mind ran. There is something almost unbearable about that image now, knowing what came after. A man sitting in the warm noise of a Polish cafe in the 1930s, at the center of a circle of brilliant friends, doing some of the deepest mathematics of the century in an atmosphere of pure conviviality, with absolutely no way of knowing that within 10 years most of that circle would be scattered across the earth or dead. the cafe gone, the city itself renamed and emptied of the people who had made it what it was. The mathematics they produced in those years was extraordinary in its sheer density. A small number of men in a single provincial city reshaped functional analysis, topology, measure theory, and the foundations of mathematics, and they did it largely sitting around a few marble tables, talking. And the talk that produced the doubled ball was happening in exactly that room, among exactly those people, in the few short years before the room and the people were taken apart. The younger of the two men whose names are on our theorem arrived in this world from a different direction entirely. Alfred Tarski was born in Warsaw in 1901, and he was not born Alfred Tarski. He was born Alfred Teitelbaum into a Jewish family and as a young man. In 1923, he and his brother changed their surname to Tarski, a name they essentially invented because it sounded authentically Polish, and Tarski converted to Catholicism, though he was by all accounts a committed atheist who believed in no God at all. He did these things for one reason. Anti-Semitism in Polish academic life was severe and rising, and a man named Teitelbaum would find doors closed that might open for a man named Tarski. He made a calculated decision to file off the part of his identity that the world would punish him for. There is a story, and it may be polished by retelling, but it captures something true, that years later, in America, Tarski was sitting in a seminar when another mathematician mentioned that a certain result had already been obtained by someone named Teitelbaum. Tarski stood up and said, "I am Teitelbaum." The name he had buried to survive, spoken aloud by a stranger who did not know it was his. Tarski was a logician of ferocious rigor, and he and Banach were a strange pairing, the intuitive natural genius and the precise architect of logic. But in 1924, they wrote a paper together with a title that, translated from the French, reads roughly as on the decomposition of sets of points into respectively congruent parts. It was published in the journal Fundamenta Mathematicae, the journal the Polish school had founded to give their work a home. And here is the detail that almost everyone gets exactly backwards. Banach and Tarski did not present their result as a wonderful discovery. They present it, in part, as a problem. They understood that doubling a ball was absurd, that it violated everything reasonable, and they understood precisely which assumption in the foundations of mathematics had let the absurdity through the door. It was the axiom of choice, Vitali's move, the reaching into infinitely many boxes. They were holding up their own theorem like a piece of evidence and saying, in effect, look what this assumption forces us to accept. They were pointing at the foundations and telling everyone that something down there did not add up. Most of the mathematical world looked at where they were pointing, understood the problem completely, and decided to keep the assumption anyway. Hold on to that. The men who proved it may have meant it as a warning, and the warning was overruled. And the thing they were warning about is the thing this whole story is descending toward. Then the world the Wow school lived in came apart. In September of 1939, Germany invaded Poland from the west, and the Soviet Union invaded from the east, and Wow fell under Soviet control. Tarski was not there to see it. In August of 1939, weeks before the invasion, he had boarded a ship called the Pilsudski and sailed for New York to attend a conference on the unity of science at Harvard. It was, as it turned out, the last ship to leave Poland for the United States before the war closed the ocean behind it. He went expecting to be gone for a few weeks. He left behind his wife Maria and their 2 young children. He would not see them again for 7 years. Almost his entire extended family, the Teitelbaums he had renamed himself away from, would be murdered in the Holocaust. Tarski survived because of the timing of a single voyage, and he spent the war in America, eventually settling at Berkeley. Building a new life on the far side of an ocean while everything he had left behind was destroyed, not knowing for years whether his wife and children were alive. Banach stayed in Wow, and what happened to him is one of the strangest survival stories in the history of science. When the Germans took the city from the Soviets in 1941, the universities were shut and the Polish intelligentsia were marked for elimination. Banach survived by becoming a lice feeder. There was an institute in Wow run by a biologist named Rudolf Weigel that produced a vaccine against typhus, and the production of that vaccine required feeding human blood to infected lice. Men would strap small cages of lice to their legs and let the insects feed on them through a fine mesh. It was unpleasant, it carried real risk of infection, and it was also one of the only forms of employment that came with documents protecting the holder from deportation and execution, because the Germans wanted the typhus vaccine for their own troops. So one of the greatest mathematicians of the 20th century spent the war letting lice drink his blood in order to stay alive, and it worked, and he was alive when the Soviets retook the city in 1944. He did not get to enjoy it. Banach had been diagnosed with lung cancer, and on the 31st of August, 1945, with the war in Europe just months over, he died in Wow at the age of 53. His funeral was an enormous public event, a gathering of a vanishing world. He was buried in the Lichako cemetery in the city he had made the center of a mathematical universe. There is an irony in how Banach is remembered that I cannot leave alone. I told you at the start that one of the two men who proved this theorem has an entire branch of modern mathematics named after him, and it is Banach, and the thing named after him is not the doubled ball. It is the Banach space. In the years before the war, Banach built the foundations of what we now call functional analysis, the study of infinite dimensional spaces. Spaces whose points are not positions but entire functions, whole curves treated as single objects sitting in a geometry of their own. It sounds impossibly abstract, and it is the quiet machinery underneath enormous amounts of modern mathematics and physics, underneath quantum mechanics, underneath signal processing, underneath the mathematics that runs through technologies you use today without thinking. A Banach space is one of the central objects a mathematics student meets, named for the laundress's son from the park bench. And most students who work with them every day have no idea that the same man, almost as a side project, once proved that a ball can be cut into 5 pieces and made into 2. The doubling was, for Banach, close to a footnote. It is the thing the public remembers, and it is nearly the only thing, and it is not what he gave mathematics. What he gave mathematics was a whole new place to stand, and then the place he physically stood was erased from the map, and he died of cancer in a city that within a few years would not even keep its name. The others did not all survive even that far. On the nights of the 3rd and 4th of July, 1941, in the first days of the German occupation of Wow, SS units and their auxiliaries rounded up Polish professors and took them to a place called the Wulecki Hills and shot them. 25 academics were murdered there, along with roughly 25 of their family members and others who happened to be present, in a single coordinated massacre aimed at destroying the city's intellectual life at the root. Among the dead was Antoni Lomnicki, who had been an early mentor to Banach. Other mathematicians of the school were killed elsewhere or took their own lives rather than be taken. And Felix Hausdorff, the gentle poet who had doubled the sphere in 1914, the man who started all of this, did not escape either. He was Jewish, in Germany, an old man by the time the Nazis came to power, and he was stripped of his professorship and increasingly trapped as his efforts to emigrate failed. In January of 1942, Hausdorff received the order that he, his wife Charlotte, and her sister were to be sent to an internment camp, which everyone understood by then was the antechamber to something worse, on the 26th of January, 1942. The three of them took fatal doses of a barbiturate together rather than go. In a farewell letter to a friend, Hausdorff wrote with the dark, punning wit of the poet he had once been, a line that turns on the name of the camp, Endenisch, which contains the German words for the end. Even Endenisch, he wrote, is perhaps still not the end. The man who proved that a sphere contains two copies of itself, that there is always more inside than there should be, died because the world he lived in had decided there was no longer any room in it for him at all. There is one survivor from that world I have not told you about, and it is not a person. It is the notebook. The Scottish book, the cheap-bound notebook that Banach's wife had bought and left with the head waiter, the one the mathematicians filled with problems and prizes between cups of coffee, survived the war that killed so many of the men who had written in it. As the catastrophe closed in on Wow, the book was hidden and kept safe, buried for a time by some accounts, carried through the occupation by people who understood that it was worth protecting with their lives. After the war, it surfaced again. Steinhaus, who had survived the occupation in hiding under a false name, got hold of it, copied it out by hand, and sent that copy across the ocean to Stanislaw Ulam, the same Ulam who had sat at those tables as a young man and who was now in America at the center of the work on the bomb. Ulam translated it into English, and the Scottish book entered the wider world, and its problems went on to shape mathematics for the rest of the century, the goose problem among them. Think about the asymmetry in that. The notebook outlived most of its authors. The marble tables were gone, the cafe was gone, the city had been renamed, and its people scattered or murdered, and the one thing that came through whole was the written record of the questions they had asked. The men who proved that you can always pull more out of a thing than you put into it were themselves subtracted from the world almost entirely, and what remained was a list of unanswered problems in a cheap notebook. The ideas outlived the people. That is either the most hopeful thing in this entire story or the most desolate, and I have honestly never been able to decide which. And I have stopped trying to. I have to stop here, because the contrast is almost unbearable and I do not want to rush past it. These men proved that you can take one world and pull a second identical world out of its pieces, that there is a hidden surplus folded into the structure of space, an extra ball waiting inside every ball. And then they lived through a period of history that did the precise opposite to them. That took a whole and subtracted until almost nothing was left. The mathematics says you can always get more out than you put in. Their lives said the opposite, with a cruelty that no theorem can touch. And the assumption that made their theorem possible, the axiom of choice, the thing they may have meant as a warning, was still sitting there in the foundations after all of them were gone, switched on, doing its work, waiting for the rest of mathematics to decide what to do about it. That decision is the next thing you need to understand, because the axiom of choice is not like the other rules of mathematics. It is the one rule that mathematicians got to vote on, and the vote is the most disturbing part of this entire story. In 1904, a German mathematician named Ernst Zermelo proved something that the entire mathematical world had wanted proved for years. And he proved it using an assumption so quiet that he almost slipped it past everyone, and when they noticed it, the argument that broke out lasted, in a sense, for the rest of the century. The thing he proved was called the well-ordering theorem, and the assumption he used was the axiom of choice. And you need to understand both, because they are the hinge that the entire weight of this story swings on. The axiom of choice says something that sounds, at first hearing, almost too obvious to bother stating. Suppose you have a collection of boxes, and every box has at least one thing in it. The axiom of choice says you can choose one thing from each box. That is the whole statement. From a collection of non-empty boxes, you can select one item out of each and gather your selections into a new set. When there are finitely many boxes, nobody objects, because you can just do it one box at a time and finish. When there are infinitely many boxes, but a rule tells you what to pick, nobody objects either. If you have infinitely many boxes, each containing numbers, and you say always pick the smallest, that is a rule. It picks for you, no axiom required. The trouble, the entire trouble, the trouble that holds the doubled ball inside it, arrives when there are infinitely many boxes and there is no rule. When the boxes are so wild and so numerous that no formula, no description, no procedure of any kind can tell you which item to take from each one. The axiom of choice says you can make the selection anyway, all at once. Infinitely many arbitrary picks, with no rule guiding a single one of them, producing a finished set that nobody can describe, that no one could ever write down, that exists for no reason other than that the axiom says it exists. There is a way to feel how strange this axiom is, and it comes through the very thing Zermelo first used it for. He used the axiom of choice to prove the well-ordering theorem, and here is what that theorem says. Take any set at all, no matter how large or how wild, and you can arrange all of its elements in a line, in an order, such that every collection of them you could ever point to has a first element, a smallest one, a definite beginning. For the counting numbers, this is obvious. 1 comes first, then 2, then 3, and any bunch of them you grab has a least member. But the well-ordering theorem says this can be done for any set whatsoever, including the set of all real numbers, the entire continuous number line. And that should stop you cold. Think about the real numbers between 0 and 1. What is the smallest one? There is no smallest one. After 0, there is no next number, because between 0 and any candidate you name there are infinitely more, crowding in towards 0, with no gap and no first step. The real line has no natural beginning, no second element, no orderly succession from one number to the number just after it. It is the very image of the smooth and the seamless, the thing that flows without joints. And yet the well-ordering theorem, powered by the axiom of choice, insists that the real numbers can be rearranged into an order that does have a first element, and a definite next element after every element, and a smallest member inside every collection you could ever describe. Such an ordering must exist. The axiom guarantees it. And here is the blade. Nobody can show you one. No human being has ever written down a well-ordering of the real numbers, and no human being ever will. It cannot be captured by any formula, cannot be exhibited, cannot be constructed by any procedure. It is exactly the same ghost as the Vitali set and the pieces of the doubled ball, the third appearance of a single move. Vitali reached into infinitely many families and chose, and produced a set no one can describe. Zermelo reached into the real numbers and ordered them, and produced an ordering no one can describe. Banach-Tarski reached into the orbits of the rotations and chose, and produced pieces no one can describe. 3 times the same hand reaches into the infinite. 3 times it comes back holding something, and 3 times, when you ask to see what it is holding, there is nothing to show you. The axiom of choice swears the thing is there and then declines to produce it, and mathematics accepts the oath and never asks for the evidence again. That is what the French objectors could not bear. An existence with no example, a truth with no witness, a thing that is real by decree and never once by demonstration. That is what Vitali did when he picked one number from each family. That is what Banach-Tarski did when they anchored their pieces by selecting one point from each orbit of the rotations. The non-measurable pieces of the doubled ball cannot be described. There is no equation for them. You cannot draw them, cannot specify them, cannot point to a single one of their points and say, here is one, here is another. They are conjured into existence entirely by the axiom of choice, which asserts that a selection was made without ever telling you or itself what the selection was. They are the most real things that can never be seen. This is exactly what a group of French mathematicians could not stomach. In 1905, in an exchange of letters that became famous as the 5 letters on set theory, 3 of the finest analysts of the age, Émile Borel, René Baer, and Henri Lebesgue, the same Lebesgue whose measure we have been talking about this whole time, argued bitterly about what the axiom of choice even meant. Their objection was philosophical, and it was deep, and I think it has never really been answered. For them, to say that a mathematical object exists should mean that you can define it, describe it, pin it down with a finite amount of language. An object you can prove exists but can never describe, an object conjured by pure assertion, was to them not really an object at all. It was a ghost. Lebesgue in particular held that a mathematical thing exists only when it has been defined uniquely in words. Borel looked at the consequences of the axiom, looked later at exactly the kind of paradox Banach-Tarski produced, and treated it not as a wonderful theorem, but as a proof that something had gone wrong. If your assumption lets you double a ball, the assumption is the problem. Throw it out. But they could not throw it out, and this is the moment the whole story turns, so I am going to slow all the way down. They could not throw out the axiom of choice, because mathematics had quietly become dependent on it. Not in one place. Everywhere, some of the most important and most useful theorems in modern mathematics turn out to need the axiom of choice, or some piece of it, to be proved at all. The statement that every vector space has a basis, which sounds technical but underwrites enormous areas of mathematics and physics, requires the axiom of choice. A theorem called Tychonoff's theorem, which is foundational to topology, is actually equivalent to the axiom of choice, the same statement wearing a different coat. The Hahn-Banach theorem, named in part for our own Stefan Banach, a cornerstone of the functional analysis he founded, leans on it. Pull the axiom of choice out of mathematics, and a startling amount of the building comes down with it. Whole fields lose their central results. Theorems that everyone is certain are true become unprovable. The price of refusing the axiom is not that you lose the doubled ball. The price is that you lose half of modern mathematics along with it. So the mathematical community faced a genuine dilemma, and I want you to feel it as the real choice it was. Accept the axiom of choice and keep almost all of the mathematics you care about, and in exchange accept that a solid ball can be cut into 5 pieces and reassembled into 2. Or reject the axiom of choice, banish the doubled ball, restore your intuition about volume, and in exchange give up the basis theorem, give up Tychonoff, give up large parts of analysis and topology and algebra, and watch the cathedral of 20th century mathematics lose its load-bearing walls. Those were the terms. There was no third door, no version where you keep everything you want and lose only the thing you hate. The mathematical world chose the ball. It chose to keep the axiom of choice, to keep the useful mathematics, and to swallow the doubled sphere as the cost. This is the vote I told you about. It was not a literal vote with ballots, but it was a real collective decision, made over years, settling into the standard foundations of mathematics so thoroughly that today the axiom of choice is simply part of the default system, the system called Zermelo-Fraenkel set theory with choice. The water that essentially all working mathematicians swim in without thinking about it. They looked at a theorem that says you can create something from nothing, understood that it followed directly from an assumption they were making, understood that the assumption was optional, and decided to keep making the assumption because the alternative was worse. They chose to live in a mathematics where the ball can be doubled because the mathematics where it cannot be doubled was too poor to live in. I want to trace what happened to the result after that choice, because the trajectory is its own quiet scandal, and it took decades to complete. When the doubled ball first appeared in 1924, the people who cared about foundations understood it as an alarm. Borel and the others who already distrusted the axiom of choice pointed at it and said, "There, that is what your axiom does. It manufactures balls out of nothing. Throw it out." It was a live controversy, a genuine crisis at the bottom of mathematics, exactly the kind of thing that should have stopped the discipline in its tracks and forced a reckoning. And for a while it was treated that way, argued over, worried about, taken seriously as a threat. But mathematics needed the axiom too badly to throw it out. And slowly, over the middle of the century, something subtle happened to the way the result was discussed. It got reclassified. It stopped being an alarm and started being a curiosity. The word that did most of the work was the word paradox itself, because to call a thing a paradox is to file it under amusements, under brain teasers, under things that are surprising but finally harmless, rather than under refutations, under crises, under things that demand you change what you are doing. By calling it the Banach-Tarski paradox, instead of the Banach-Tarski refutation of naive volume, the discipline quietly gave itself permission to enjoy the result, rather than be disturbed by it. And that is roughly where it sits today. The doubling of the ball is now a piece of mathematical folklore. The thing a professor shows first-year students to make them gasp, a staple of popular mathematics videos and books, presented almost always as a delightful absurdity, a fun fact about infinity, a magic trick that the universe happens to permit. The framing is gentle, and the framing is deliberate, even though no single person ever sat down and decided it. The result that two of the founders of modern Polish mathematics may well have built as a warning about the foundations has been polished, across 100 years, into entertainment, into the mathematical equivalent of a card trick, precisely because the alternative, sitting with what it actually says about the ground under everything, is so much harder to do. This is not a conspiracy. Nobody banned the truth. It is something quieter and more human than a conspiracy, the slow drift of an entire field toward the version of a story that lets everyone keep working without flinching. The warning was not refuted. It was defanged by being made charming, and the most effective way to bury an uncomfortable truth was never to hide it. It was to put it on display, label it a curiosity, and let everyone walk past it on the way to something else. And here, finally, is the question that should be making you uneasy. The one I have been steering toward since the first minute. They got to choose. Think about what that means. We are not talking about taste in restaurants. We are talking about the foundations of mathematics, the thing that is supposed to be the most certain, the most necessary, the most not up to us of all human knowledge. 2 + 2 is 4 whether you like it or not. The angles of a triangle behave the way they behave whether you vote for it or not. Mathematics is supposed to be the one place where there is no choosing, where things are simply true and you submit to them. And yet at the very bottom, in the foundations, there sat a statement that you could take or leave that produced one mathematics if you took it and a different mathematics if you left it. And the difference between those two mathematics was nothing less than whether the impossible was true, whether a ball could become two balls, which raises a question that sounds almost childish until you realize it has no answer. Fine, they chose to keep the axiom. But is it true? Not useful, not convenient. true, is it actually the case, out there in whatever realm mathematical facts live in, that you can choose one element from each of infinitely many boxes with no rule? Is the axiom of choice a true description of the mathematical universe, or just a convenient fiction we agreed to because the consequences of honesty were inconvenient? You would think that this, of all questions, mathematics could answer. You would think that the field whose entire purpose is to prove things could at least prove whether one of its own foundational assumptions is true or false. It cannot, and the proof that it cannot is the strangest result in this entire story. Stranger than the ball, stranger than the Vitali monster, stranger than anything Hausdorff found on the surface of his sphere. Because in the middle of the 20th century, two men, working 25 years apart, proved together that the question is unanswerable, not unanswered. Unanswerable, they proved that mathematics is constitutionally incapable of deciding whether the axiom of choice is true, and in doing so, they proved something far worse. Something that I think is one of the most quietly devastating facts that human beings have ever established about the limits of their own knowledge. The first of the two was Godel, and in 1938 he proved one half of the trap. Godel showed that you cannot disprove the axiom of choice. He did it by building a mathematical universe from the ground up, a carefully constructed model of set theory that he called the constructible universe, in which only the sets that can be built up step by step according to strict rules are allowed to exist. Inside that universe, he showed, the axiom of choice is true, and so is everything else in the standard foundations, with no contradiction anywhere. The meaning of this is sharp. If accepting the axiom of choice led to a contradiction, that contradiction would have to show up inside Godel's universe too, and it does not. So the axiom of choice cannot be the source of any contradiction. You can never prove it false. That door is closed forever. For 25 years, that was where matter stood. The axiom could not be disproven, but nobody could prove it either, and there was no known way to settle the other half of the question. Then, in 1963, a young American mathematician named Paul Cohen, who was not even a set theorist by training, invented an entirely new technique to do something that had been thought impossible. The technique is called forcing, and it is one of the genuine landmarks of 20th century thought, a method for constructing new mathematical universes by carefully adding new sets to an existing universe, sets whose properties you can control with surgical precision. Using forcing, Cohen built a universe in which the axiom of choice is false, a complete, consistent mathematical world in which you cannot always choose one element from each of infinitely many boxes. And because that world is also free of contradiction, the axiom of choice can never be proven true. That door closed, too. Cohen won the Fields Medal in 1966 for this work, the highest honor in mathematics, and to this day it is essentially the only Fields Medal ever awarded for pure mathematical logic. I want to tell you a little about Paul Cohen, because his place in this story is stranger and more human than the result alone suggests. He was not a logician. He was an analyst, a specialist in a different and far more concrete part of mathematics, a brilliant and famously competitive young man at Stanford, and he came to the axiom of choice and the continuum problem almost as a private dare, the way a climber looks at a wall nobody has climbed. The people who actually lived in the foundations had been stuck on these questions for decades. Cohen, the outsider, invented forcing more or less from nothing in order to break through, and the method was so new and so strange that at first hardly anyone could tell whether it was even valid, because it did not resemble anything the field had ever seen. So Cohen did the thing you do when you have built something at the very edge of what can be proven, and you need to know whether the ground under it is real. He took it to Godel. Godel, by then, was the reigning authority on precisely these questions, the man who had proven the first half of the answer 25 years before, and he was also increasingly reclusive, hard to reach, wary of nearly everyone. Cohen brought his proof to Godel at Princeton, and Godel read it, and Godel, who did not give his approval lightly to anyone, confirmed that it was correct. There is something almost ceremonial in that, the man who closed the first door personally certifying the man who closed the second, the two halves of one impossibility meeting in a single room. Godel then helped push the work into print quickly, easing its path into the world. And forcing went on to become one of the central instruments of modern set theory, the tool with which logicians have since proven question after question to be undecidable. Each new proof, another quiet door swinging shut, another thing we are now certain we will never get to know. Put Godel and Cohen together, and you get the result that should change how you think about what mathematics even is. The axiom of choice can be neither proven nor disproven from the other rules of mathematics. It is independent. It floats free. And this means there is not one mathematics. There are at least two. There is a mathematics in which the axiom of choice is true. And in that mathematics, a ball can be cut into 5 pieces and reassembled into 2 balls. And there is a mathematics in which the axiom of choice is false. And in that mathematics it cannot. Both of these mathematics are completely consistent. Neither contains a contradiction. Neither is more logically valid than the other. They are 2 equally legitimate descriptions of the mathematical universe, and they disagree about whether the impossible is true, and there is no fact, no proof, no argument available from within mathematics that can tell you which one is correct. You do not get to find out. The question of whether you can really double a ball is not hard. It is decided by which universe you choose to stand in, and the choice is not forced by logic. It is yours. And then Robert Solovay made it worse, in 1970, in a way that I find almost too clean. Solovay built, using these same techniques, a mathematical universe in which every single set of real numbers is measurable. Every set has a size. Vitali's monster cannot exist there. The non-measurable pieces of the doubled ball cannot exist there. In Solovay's universe, volume is conserved exactly the way your childhood intuition always insisted it must be. You cannot get more by cutting. The floor never comes up. And the Banach-Tarski theorem is simply false. And here is the thing. Solovay's universe is as consistent as ours. It is not a fantasy or a degenerate special case. It is a coherent, fully functioning mathematical reality in which the doubled ball is an impossibility, sitting right next to our reality in which the doubled ball is a theorem, and the only difference between them is a decision about the foundations that logic refuses to make for you. The second world that Banach and Tarski pulled out of the pieces of the first turns out to be real in a way they never intended. There genuinely is another mathematics next to ours, identical in almost every respect, in which their theorem never happened. I want to slow down on what these universes actually are, because the word universe is doing real work here, and it is easy to hear it as a figure of speech when it is not one. When a logician like Cohen or Solovay builds a model of set theory, they are not telling a story or imagining a hypothetical. They are constructing, with full rigor, a complete mathematical world, a collection of sets that obeys all the basic axioms, and then proving that inside that world a particular statement comes out true or comes out false. Cohen's method, forcing, is a way of starting with one universe and carefully adjoining new sets to it, new objects whose properties you pin down in advance through an elaborate bookkeeping of conditions, until you have grown a larger universe in which the thing you wanted is now the case. It is, in a real sense, a technique for constructing mathematical reality to order, and it works, and it has been used ever since to settle dozens of questions that turned out to be undecidable by the standard axioms, true in some universes and false in others. The most famous of those questions is older than the doubled ball. It is called the continuum hypothesis, and it asks whether there is any size of infinity strictly between the infinity of the counting numbers and the larger infinity of the real numbers. Cohen proved that one independent too, with the same forcing technique, in the same handful of years in the early 1960s. And it was the main reason he received the Fields Medal. And what has slowly settled over set theory in the decades since is the recognition that these are not a few isolated freak questions. This may simply be the normal condition of mathematics at the bottom. There is not one fixed universe of sets that we are gradually mapping like explorers filling in a coastline. There is something far stranger, a vast landscape of possible universes which set theorists now sometimes call the multiverse. Each one a different consistent way the foundations could be. The universes differing from one another on the axiom of choice, on the continuum hypothesis, on the existence of unimaginably large infinities, on whether the ball can be doubled. Some of these worlds can double the ball, some cannot. As far as logic is concerned, they are all equally real, equally legitimate, equally entitled to the name mathematics. We are standing in one of them, the one our textbooks happen to describe, and we cannot prove it is the true one, because the phrase "the true one" may not point at anything at all. There is one more piece, and it tells you exactly where the curse lives, and it should unsettle you specifically. The doubling works in 3 dimensions. It does not work in 1 dimension or 2. You cannot double a line segment, and you cannot double a flat disk. Banach himself proved this early on, that on the line and on the plane you can in fact assign a consistent size to every set, that the conservation of length and area can be saved completely. The reason is buried in the rotations. The mathematician John von Neumann worked out, in 1929, that what matters is whether the group of motions is what is now called amenable, a tame kind of group that cannot contain the wild branching free group we built earlier. The rigid motions of the line and the plane are amenable. They are tame. There is no free group hiding inside them, so there is no doubling. But the rotations of 3-dimensional space are not amenable. The free group is in there, with its endless forking branches, and the moment you have 3 dimensions to rotate in, the curse switches on. Below 3 dimensions, your intuition is exactly correct, and volume is safe. At 3 dimensions, it breaks. And 3 dimensions is where you live. The number of dimensions of the space your body occupies, the space the ball occupies, the space everything you have ever touched occupies, is precisely the smallest number of dimensions in which a solid object can be cut apart and rebuilt into 2 of itself. We live 1 dimension past the safe zone. We live in the first world where it can happen. I told you the plane is safe, and it is, but I have to qualify that, because the safety turns out to be more fragile and more revealing than it first appears. The plane is safe only for as long as you restrict yourself to rigid motions, to sliding and turning without ever distorting. That restriction is precisely what keeps the group of moves amenable, tame, free of the branching monster. But the same John von Neumann, who explained all of this, asked what happens if you loosen the restriction by just a little. Suppose you allow yourself, in the flat plane, not only rigid motions, but area-preserving distortions, the shears and stretches that squash a shape in one direction while stretching it in another, so that the total area comes out unchanged. These still feel gentle. Each one preserves area exactly, to the last decimal. And von Neumann proved, in 1929, that this slightly larger collection of moves does contain a free group, the branching tree, hiding among the shears, which means the plane becomes paradoxical after all. You can take a region of the plane, cut it into non-measurable pieces, and reassemble those pieces by these area-preserving distortions into two copies of the region, even though every individual move you made preserved area perfectly. Conservation survives each step and dies in the whole. So the real lesson is not that 2 dimensions are safe and 3 are cursed, as though the number itself carried the spell. The lesson is that the curse was never about dimension at all. It was about whether the moves you permit yourself are rich enough to conceal a free group. 3-dimensional rotation is simply the most innocent and most natural place where that richness shows up without your having to distort anything, where the monster is already living inside the plainest motion there is, the turning of a solid object in space. The flat plane keeps its safety only through your agreement not to reach for the moves that would break it. The 3rd dimension does not offer you that agreement. The free group is already there the instant you are allowed to rotate, and you have been allowed to rotate your entire life. There is even a flat version of the strangeness, found much later, that I cannot leave out because of who set it in motion. In 1925, Tarski asked whether you could cut a disk into pieces and rearrange them into a square of the same area, a problem that became known as squaring the circle by dissection. It sat open for 65 years. In 1990, a Hungarian mathematician named Miklos Lackovic proved that you can, that a disk can be cut into pieces, by his own estimate something on the order of 10 to the 50th power of them, and reassembled into a square using only sliding, no rotation needed at all. The pieces are non-measurable, the children of the same axiom. Because area is preserved in the plane, this is gentler than the doubled ball. It does not create anything from nothing, but it is the same machinery, the same conjured invisible pieces, the same fingerprint of the axiom of choice on the structure of space. And the man who posed that problem, the man whose question rippled across the 20th century until it was answered in 1990, was the same Alfred Tarski whose name sits on the doubled ball, the same man who had once changed his name to survive. He had one more thing to prove about the limits of what can be known, and it is the darkest result in this story, and it is the place where we end. You have been told your whole life that mathematics is the one thing that is certain. When everything else is opinion and politics and shifting ground, 2 + 2 is 4. And the proof is the proof, and that is where you can finally stand. I want to tell you what the people who actually built the foundations found when they dug down to the bottom to check, because it is not what you were promised, and they have known it for almost 100 years. To feel the weight of what came next, you have to know what it was done to. At the turn of the 20th century, mathematics had just been through a fright. A young Englishman named Bertrand Russell had found a contradiction sitting in the middle of the brand new theory of sets. A simple question about whether the set of all sets that do not contain themselves contains itself. A question that answers yes if it answers no, and no if it answers yes. It was a crack in the foundation, discovered just as the foundation was being poured, and it frightened people. Because if set theory could contain a contradiction, then so, perhaps, could everything built on top of it, which was beginning to be all of mathematics. Out of that fright came a determination to make mathematics safe forever, and the man who led it was the greatest mathematician of the age, David Hilbert. Hilbert had a dream, and the dream had a name. It was called Hilbert's program, and its goal was to make mathematics absolutely, permanently, provably secure. He wanted to show that all of mathematics could be built on a finite list of axioms, that those axioms would never contradict each other, that this freedom from contradiction could itself be proven with complete certainty, and that every true mathematical statement could in principle be reached by proof from the axioms. A complete and consistent and final foundation, a fortress with no cracks, into which no contradiction could ever enter and from which no truth could ever escape unproven. Hilbert believed this was achievable, and he believed it with something close to faith. In a radio address in 1930, in the city where he was born, he rejected the idea that there could be questions mathematics would never answer. And he ended with a line that was later carved onto his gravestone. "We must know. We will know." He said it almost to the day that a quiet 24-year-old logician at a conference in the very same city presented a result that would prove him wrong forever. The timing has the quality of a tragedy arranged by someone with a cruel sense of structure. Hilbert stood up and declared that we will know, and within about a day, the proof that we can never know all of it was already in the room. The logician was Godel. In 1931, before any of the work on the axiom of choice was finished, Godel had already proven the two incompleteness theorems, and they broke the dream that mathematics could ever be made fully secure. The first says that any mathematical system rich enough to do ordinary arithmetic contains true statements that it cannot prove. Not hard to prove. Impossible to prove. From inside that system, forever. The second is worse. It says that no such system can prove its own consistency. Mathematics cannot, from within, guarantee that it does not contain a contradiction. The thing you were told was the bedrock cannot certify its own ground. It can only ever be trusted from somewhere outside itself, and there is no final outside. I want to tell you how Godel died, because I have never been able to separate it from what he proved, and I think the connection is real even though I cannot make it into an argument. Godel proved that no system can guarantee its own safety from within, that consistency can only ever be certified from somewhere outside, and that there is no final outside that certifies everything. He spent his last years at Princeton, increasingly alone, increasingly afraid. He became convinced that he was being poisoned, that the food around him could not be trusted, and the only person whose food he would eat was his wife Adele, who tasted his meals for him and stood between him and a danger that existed only in his mind. In late 1977, Adele was hospitalized for 6 months. With the one person he trusted gone, Godel stopped eating. He starved himself, slowly, unable to accept safety from any source he could not verify. And in January of 1978 he died. The hospital recorded his weight at 65 pounds. The cause of death was given as malnutrition and inanition brought on by personality disturbance. The man who proved that a system cannot trust itself from the inside and cannot find a final ground outside itself died because he could not trust anything outside himself to be safe, and could find no ground to stand on at all. I do not offer that as a theorem. I offer it as the kind of rhyme that history sometimes makes, and that, once you have heard it, you cannot stop hearing. Hilbert's fortress was never built. After Godel, everyone understood that it could not be built, that the dream of a complete and self-certifying mathematics had been impossible from the start, that the most rigorous form of knowledge human beings have ever constructed could not, in the end, vouch for itself. Mathematics did not collapse. It went on, exactly as productive and exactly as useful as before. But the people working at the very bottom of it, in the foundations, knew something the rest of the world was never told. They knew the floor did not reach all the way down. The axiom of choice is one face of this. It is a statement that mathematics can neither prove nor refute, that produces a ball doubling itself in one universe and conservation of volume in another, with logic standing back and declining to say which universe is the real one. The doubled ball is not a curiosity off to the side of mathematics. It is a place where the floor goes transparent and you can see straight down through it, and what is underneath is not more floor. What is underneath is a choice, unforced, undecidable, ours. The most certain thing in human thought rests, at the bottom, on a decision that the certainty itself cannot justify. And then there is Tarski, and the last thing he proved. The thing I have been holding back. The man whose name is on the theorem that creates two worlds from one, the man who erased the name Teitelbaum to walk through a door, proved a theorem about truth itself, and it is called the undefinability of truth. What Tarski showed in the early 1930s is that a sufficiently powerful mathematical language cannot define its own notion of truth. A system cannot contain a statement of what it means for its own statements to be true. To talk about the truth of a language, you have to step up into a richer language above it, and to talk about the truth of that one, you have to step up again, forever, with no top floor, no final language in which truth simply rests and is itself. The same man who proved you can pull a second ball out of the first proved that mathematics cannot speak its own truth. It can prove things without end. It can never turn around and say, from the inside, here is what it means for all of this to be true. Truth, for a formal system, is always one level up. In a room the system can never enter. To see why a system cannot hold its own truth, you only need the oldest trap in logic, the sentence that says of itself, this sentence is false. If it is true, then what it claims holds, so it is false. If it is false, then what it claims fails, so it is true. It spins forever, true demanding false demanding true, and for most of history it was treated as a clever toy. A riddle to annoy students with. Tarski saw that it was not a toy. He saw that it was a weapon, and he saw exactly what it could destroy. He proved that if a mathematical language were powerful enough to contain its own definition of truth, then you could build precisely that sentence inside it, a sentence that asserts its own falsehood in the system's own terms, and the entire system would tear itself apart into contradiction. So no consistent system rich enough to talk about itself is permitted to contain its own notion of truth. The liar sentence is not a paradox waiting to be solved. It is a wall, and Tarski was the one who measured it and proved it could never be climbed from the inside. There is something almost too pointed about this proof coming from Tarski in particular, and I have to say it even though it is not mathematics. Here was a man who had changed his own name, who had once stood in a room and heard a stranger casually speak the name he had buried, Teitelbaum, and who stood up and claimed it out loud. A man who spent his whole life moving between identities, the Jewish child and the invented Polish surname, and the American professor, who knew better than almost anyone alive that what a thing is called and what it is are not the same thing, and that the truth about a person can sit just outside the language that person is permitted to use about themselves. He proved that mathematics is caught in the same predicament he had lived, that a system can be perfectly true and structurally unable to say so, that truth can be real and permanently out of reach of the very thing it is true about. He was reunited with his wife and children in 1946 after 7 years and an ocean and a war that murdered nearly everyone else with his name. And he lived out his life at Berkeley as one of the towering logicians of the century, exacting and difficult and luminous, and he died in 1983. The undefinability of truth is now a standard theorem, taught to graduate students as a cornerstone of modern logic. The man who proved you can cut a ball into two balls, and the man who proved that a system cannot speak its own truth, and the man who refused to let a stranger keep the name he had hidden in order to survive, were one person. So look at what this story actually leaves in your hands. A solid ball can be cut into 5 pieces and made into 2. That is a theorem, proven, permanent, not in dispute. It is true because of an assumption that cannot be proven or disproven. An assumption mathematicians kept on purpose because the honest alternative was poorer. An assumption that is false in another mathematics exactly as real as ours. The pieces that do the doubling cannot be described, cannot be drawn, cannot be exhibited, and exist only because a rule asserts that a choice was made that no one can ever specify. The whole structure sits on foundations that by the proofs of the very men who built them cannot prove their own consistency and cannot define their own truth. And all of it lives one dimension above the safe zone, in 3-dimensional space, the exact space your body occupies right now. I told you at the start that there were 3 things you believed. That cutting cannot change how much there is. That volume is a real and fixed property of things. That every piece of a solid has a size. All 3 are gone. You cannot get them back by being smarter, because nothing was wrong with your thinking. They are gone because the foundations of mathematics, followed honestly to the bottom, do not support them. And the people who found this out chose to keep building anyway, and chose not to make it the headline, and went home and taught their students that 2 + 2 is 4, and said nothing about the flaw. And there is one more belief down there, older and deeper than those 3, that this story quietly takes apart, and it is the one I have the hardest time letting go of. For almost all of human history, the people who thought about mathematics assumed they were discovering it, that the truths were already out there, eternal, perfect, waiting, and that a mathematician was a kind of explorer charting a landscape that existed long before any mind arrived to see it, and would go on existing long after. The number of primes, the ratio of a circle, the theorems about triangles, none of it invented, all of it found. This is the oldest and most natural picture of what mathematics is, and it is the reason mathematics felt like the safest place to stand. You do not get to vote on a continent. It is simply there. But the axiom of choice puts a crack straight through that picture, and the crack is the doubled ball. Because here is a statement at the very foundation, and it is true in one fully consistent mathematics, and false in another fully consistent mathematics. And the difference between those 2 worlds is whether a ball can become 2 balls, and logic does not choose between them. We choose. We reached into the foundations and selected the version we wanted, the one with the better tools, and we did it knowing it came bundled with a monster. That is not the behavior of explorers charting something that was already there. That is the behavior of people building something, deciding, inventing, and yet the moment you try to settle into the comfortable conclusion that mathematics is therefore just invention, just a game we made up with rules we could have made differently, the whole thing pushes back, because it does not feel made up. It constrains us, it surprises us. It tells us things we did not want to hear and could not have guessed, the doubled ball being the clearest example, a result nobody wanted that the rules produced anyway. Invented things do not ambush their inventors like that. So you are left holding both halves, and they will not fit together. Mathematics behaves like something discovered, eternal and constraining and indifferent to your wishes. And at its very foundation, it required a choice that only invention can explain. It is somehow both, and it cannot be both, and you cannot stand outside it to see which it really is. Because Godel and Tarski already proved there is no outside to stand in. So the question of whether mathematics is discovered or invented does not get an answer. It joins the others. Is the axiom of choice true? Which universe is the real one? Was the world found or made? Not hard questions, unanswerable ones, the flaw going transparent under each of them in turn. The men in this story did not just prove that. Some of them lived it so precisely that it is hard to read as coincidence. Tarski invented a name, Tarski, chose it the way you choose an axiom for what it would let him do, for the doors it would open, and then carried underneath it a truth about who he was that the invented name could never erase and could only ever point away from. The Teitelbaum that was discovered, not chosen, that was simply and permanently the case, and that he finally stood up and spoke aloud in a room full of strangers. Invented on the surface, discovered underneath, both at once, in one man, unable to be resolved into one or the other. He proved the same thing about mathematics, that he could not stop being himself, that the chosen surface and the given depth are not two different things you can pry apart. They are the same thing, seen from inside and from outside, and there is no final outside. I told you at the start that there were 3 things you believed, and now you know there was a 4th. Here is what I am left with, and I have not found a way out of it. The certainty you reach for when everything else feels uncertain. The solid ground of mathematics, the place where things are simply true, was never quite there in the way you needed it to be. At the bottom there is a choice that logic does not make for you, a truth that the system cannot state about itself, and a second world standing next to this one, in which the impossible never happens, equally real, equally consistent, and permanently out of reach. The mathematicians know this. They have known since before the war that killed so many of them. They proved it themselves, with their own hands, and then most of them decided it was easier to live as though the floor were solid. The ball can become 2 balls. The pieces have no size. The choice cannot be justified. The truth cannot be spoken. And every one of those sentences is a theorem. You are standing on it right now.